Pressure is another physical property of matter that we can use to describe fluids. Pressure is defined as the force applied over a certain area. The units for pressure work out to be newtons per meter squared, but this is given its own SI name of pascals. One important idea to keep in mind is that there is a certain pressure being exerted on you anywhere you might be on Earth. The particles that make up the gases in our atmosphere are constantly bouncing off your body with some force. This is what is known as atmospheric pressure. Standard atmospheric pressure occurs under normal conditions when you are at sea level and has a value of 1.01 times 10 to the 5th pascals. Moving to a point that is above sea level results in less atmosphere above you and consequently a lower atmospheric pressure. Moving to a point below sea level results in more atmosphere above you and a higher atmospheric pressure. So suppose the pressure gauge on an astronaut's tank reads 6.90 times 10 to the 6th pascals. What force does the air inside the tank exert on the flat end of the cylinder tank, a disc at 0.150 meters in diameter? Since pressure is force over a certain area, we can rearrange our pressure formula to solve for the force. Now the area of a cylinder is found by multiplying the radius squared by pi. So we take half of our diameter, square that, and multiply by pi to find 0.0177 square meters. So now we know the pressure and the area and can multiply those together to get 1.22 times 10 to the 5th newtons of pressure inside of the can. Now it is important to note that the force is exerted in all directions inside the can. The fluid inside the can is considered static because it is not flowing from one place to another. It is simply filling the can and exerting its pressure. This is similar to what happens in a tire. The forces due to pressure will always be exerted perpendicular to any given surface, and the pressure will be exerted on all surfaces. So no matter where you measure the pressure in the tire, the pressure will be the same. This is also consistent with a body underwater. The fluid is being displaced by the person moving through it. If he were not there, the water would flow into that space, and as a result, the pressure is being exerted in towards him. Notice that the force vectors are drawn larger underneath. Can you guess why? If we take this glass of water, we can see that the water occupies a certain volume as found by some height, h, and the area of the cylinder, a. Now the area of the cylinder is the same on the top as it is on the bottom. However, the pressure of the water at the top is not the same as the pressure at the bottom. This is because the particles of water near the top are pressing down on the particles near the bottom, causing a higher pressure near the bottom. So what we are really interested in is how the pressure changes as we move down that column of fluid. We can look at this in terms of the forces involved as well. The force at the top of the water column is equal to the pressure times the area of the cylinder. The pressure, since it is at the top with only the air pressing down on it, is equal to the atmospheric pressure. At the bottom of the cylinder, we need to take into account that the water is also causing a pressure to be exerted. So we need to take into account the weight of that water. So the force on the bottom of the cylinder is equal to the force exerted on the top, plus the weight of the fluid above it. Now mass is sometimes not a very convenient unit to use when we have a fluid, since we may or may not be able to measure it at any given time. But we know that mass is equal to the density times the volume, so we can substitute this expression in for the mass. The rho, volume, and g represent the force applied from the weight of the fluid. Now remember, we can also substitute in the atmospheric pressure for the force at the top. Both of these expressions are the same. So if we want to figure out the pressure, we can say that the pressure at the top of the water column is equal to the force divided by the area of the cylinder. We can also say this pressure at the top is equal to the atmospheric pressure. The pressure at the bottom, then, would be equal to the total force at the bottom divided by the area, and the total force was the atmospheric pressure plus the quantity rho GV divided by area. Now V is the volume of our fluid, which in our cylinder is the area times the height. So if this gets plugged in for our volume, we can pretty quickly see that the area on the top will cancel with the area on the bottom. This leaves us with the pressure on the bottom found by adding the pressure at the top to the quantity rho GH, where the rho is the density of our fluid, g is the acceleration of gravity, and h is the height of our fluid. We want to keep in mind at this point that a lot of times we are not looking for the total pressure at the bottom, but only the change in pressure from the top to the bottom. In this case, we would not need to consider the atmospheric pressure in our calculations. This relationship holds true for liquids for great depths, since they are not really compressible. For gases, however, this relationship will only hold for a small change in depth because there's so much space in between the particles that it is very easy to compress a gas.